So in this video, we're going to go over k-nearest neighbors algorithm, looking at the classification problem for it and a regression problem for it. So for our classification problem, we're going to look at the E. coli and segmentation data sets, while for the regression, we're going to look at forest fires and machine. And also for the classification, we can look at two adaptions to k-nearest neighbors, which includes edited k-nearest neighbors and condensed k-nearest neighbors. So I'm going to choose the E. coli data set. I do provide a scaling technique to the user if they want. I'm just going to choose none. And let's look at k-nearest neighbors. So what are we looking at? So I'm performing 5-fold cross-validation on the data set. So I'll just use this one as an example. I'm actually running through where the number of neighbors equals 1 all the way up to 11. So in this one, just as an example, this is num neighbors 11. These are the prediction and actuals for each of the 5 test folds as each test fold rotates. And then from the 5-fold cross-validation, these are our individual classification errors. So what we're going to do is, we take all of these and we average them out, and that's what we get right here for the classification error. So let's look at segmentation. Segmentation, no scaling, k-nearest neighbors. So, and similar thing, right? So it looks exactly the same. So we're just going to jump right to one of our regression problems. So let's look at forest fires now, and no scaling. And I'm not prompting the user for anything else. We're just jumping right into our regression. So it looks like there's a lot more output going on, but it's similar. Same approach, right? We're going to iterate from the number of neighbors is 1 all the way up to 11. I'm printing out the predicted and actuals here for each test fold, depending on which part of the 5-fold cross-validation it is. And this time we're looking for mean squared error. So, if we actually look at the data, some of the predictions probably aren't that far off, but we have some outliers that really negatively, I would say, impact the mean squared error. And this is actually an interesting one right here, where the number of neighbors equals 11, where for one of my folds, the test folds, the mean squared error was 17,000, but for the rest, you're hovering roughly around 1,000, one of them 1749. So actually not too bad, but because of this one bad one, we got this mean squared error of 4,400 basically. But this is what the point of averaging is with the cross-validation. Otherwise, you could have had or 20% of the data just be this one and have this high mean squared error. So now let's take a look at the last one, the machine, no scaling, and we're looking at the same thing here, right? In this, it's not as bad in terms of the variation between the individual mean squared errors, but this mean squared error is pretty high, so I wonder if I scroll up a little bit, maybe to a lower number, just to see if I can find a more optimal k. And look at this, num neighbors equals 3. So here, our mean squared error could probably be lower, but there's not too much variation between them, maybe 1,500-ish to 4,600-ish. Then we got a mean squared error of 2858, which is pretty low. I bet if I scroll through this is one of the lowest mean squared errors. Now let's take a look at go back to the classification problem again. For this, let's look at E. coli, no scaling, and let's look at edited k-nearest neighbors. This is going to take a sec, but what's going to happen? In edited k-nearest neighbors, as we know, we're reducing the size of the training set. So to illustrate that, I'm actually printing out what the training size would have been if we used the whole thing, like in the regular k-nearest neighbors. And I'm also illustrating here what the new train size is, so it went down a little bit. And then we're seeing the same stuff here, basically. We're doing a 5-fold cross-validation, and then the average classification error is definitely higher than if it was the regular k-nearest neighbors. But we do have the benefit of the reduced training size we're testing on. So let's look at segmentation, and for segmentation, we'll look at the condensed k-nearest neighbors here. So this is slow again, but what's interesting is that the size of the training data is being reduced by a lot in this condensed one, where the arg train size, it looks like it's roughly 168, and it's dropping by almost 100. If I scroll up, I should find the most optimal classification error towards the beginning.